They told us it was a blur, a faint smudge streaking through the dark, barely visible, the best their billion-dollar eye in the sky could manage. When NASA released that grayscale smear of 3I Atlas, the third interstellar visitor to ever cross our solar system, the message was clear. We were lucky to see anything at all. A fast-moving speck of cosmic dust, too distant, too dim, too erratic. They gave us a JPEG, washed out and motion blurred, posted it to their outreach portal with the quiet caption, "Best available image." They expected a collective nod, a moment of awe at the distant unknown, then the scroll, the move on. But here's the thing about digital files in an open archive. They remember everything, and they talk. They speak in a language of headers and keywords, bit depths and channel descriptors, a language called metadata. NASA included that metadata when they released the file. They probably shouldn't have, because when a loose network of data archaeologists and amateur astronomers, a collective calling themselves Earth Exists, downloaded the raw archive and cracked open that code, they found a story etched in the digital fine print that contradicted the grayscale smear entirely. A story of resolution that wasn't supposed to exist, of spectral channels that vanished, of calibration protocols for an instrument that shouldn't need them. This isn't about conspiracy theories. This is about the lines of code that describe what a camera actually captured. Lines that now describe a phantom observation, a ghost image infinitely more detailed than the one you were shown. The discrepancy is impossible to ignore, and it changes everything we thought we knew about what NASA actually saw when 3I Atlas sped through our neighborhood. Stay until the end, because what's buried in those files isn't just a technical glitch. It's a question of what we're allowed to see when the universe throws something unknown at our door. But before we go any further, I need to know, are you as captivated by what's hiding in these files as I am? If you are, go ahead and like this video and subscribe to this channel. You'll want to be here when the next piece of this puzzle surfaces. Leave a comment too. Tell me where you're watching from, what hour it is in your corner of the world. There's something powerful about mapping this investigation across time zones, a reminder that this question belongs to all of us. Now, let's begin. Part 1. The metadata they didn't expect us to see. NASA told you they barely glimpsed it. They said the interstellar visitor known as 3I Atlas passed too quickly, moved too erratically, reflected too little light. The narrative was one of admirable but limited success. A camera designed to map the craters of Mars, tasked with tracking a cosmic bullet, managed to capture a faint streak. A triumph of engineering, but a scientific footnote. The image they released supports this perfectly. It looks like someone photographed a distant bird through a dirty windshield during an earthquake. It is the definition of ambiguous. They expected you to see that ambiguity and understand this is the hard edge of exploration. This is all there is. They did not expect Earth Exists. This group, a grassroots collective of digital archivists, retired engineers, and obsessive amateur astronomers, operates on a simple principle. The truth is in the raw data, and raw data is meant to be read. They began not with speculation, but with procedure. They cross-referenced observation logs from the Mars Reconnaissance Orbiter with the reported flyby date of 3I Atlas. The object was discovered by the Atlas survey on July 1st, 2025. The orbiter's high-resolution camera, HiRISE, allegedly captured it on October 2nd, 2025, during a narrow window as the object crossed Mars's orbital path. The team located the exact product identification code for that observation and pulled every associated file from NASA's planetary data system, the federally mandated, publicly accessible archive that is the bedrock of transparent space science. They found the outreach JPEG, the blurry smear we all saw. They also found the experimental data records, the EDRs, the raw, unprocessed data straight from the camera's CCD detectors. They found calibration logs, processing flags, ancillary data packages, and then they found the metadata. The metadata tells a different story entirely. The public was shown an 8-bit JPEG. For context, an 8-bit image contains 256 shades of grey, from pure black to pure white. It's the standard for consumer digital imagery, what your phone screen displays. It's sufficient for a pretty picture, but it's a blunt instrument for science, where subtle gradations matter. The metadata embedded in the raw product files, however, doesn't describe 8-bit data. It references a bit depth of 14. A 14-bit image contains 16,184 shades of grey per pixel. That is not a marginal improvement. It's a different universe of information. It's the difference between a child's crayon drawing and a medical X-ray. 14-bit imaging captures faint signals buried in noise, preserves subtle gradients invisible to the human eye, and reveals structures that vanish entirely in an 8-bit compression. If HiRise genuinely captured 14-bit data of 3i Atlas, then the blurry smear we were shown represents a catastrophic loss of information, a deliberate or negligent flattening of the dynamic range until all that remains is a vague suggestion of movement. But the anomalies don't stop at bit depth. The metadata also references multiple channel descriptors. HiRise doesn't have a single eye. It has 3 separate CCD arrays, each filtered for a different slice of light: a red band, a blue-green band, and a near-infrared band. When it images Mars, it captures data through these filters separately. Scientists then combine them to create true color composites, or false color images, that highlight geological features invisible to our eyes. This multiband capture is standard, and the metadata for the 3i Atlas observation contains references consistent with this kind of multi-channel data acquisition. Yet the public received a single, monochrome grayscale frame. Where are the other channels? If they were captured, they contain spectral information, crude color data, that could tell us if 3i Atlas is reddish like rusty rock, bluish like ice, or bright in infrared, hinting at warmth or composition. Were these channels too noisy to use? Were they never processed? Or were they processed and filed somewhere the public wasn't meant to look? The metadata raises the question, but provides no answer. Then it gets stranger. Deep in the header structures are calibration tags that reference temperature correction coefficients and radiometric scaling parameters. These are terms from the world of thermal imaging, from instruments that measure heat, not reflected light. HiRise is a visible light and near-infrared camera, a glorified, supremely powerful digital camera. It is not a thermal instrument. It shouldn't be generating thermal calibration metadata. Earth Exists speculated these could be residual template values, meaningless artifacts carried over from other instrument pipelines on the spacecraft. But they could also indicate something else, that calibration channels, designed to monitor the instrument's own temperature drift, inadvertently captured a thermal signature from the target itself. If 3i Atlas was outgassing, if it was a comet shedding heated gas and dust, its faint coma might emit a whisper of radiation in the near-infrared. The camera's calibration routine might have recorded that whisper, then treated it as instrument noise to be subtracted away. The metadata preserves the footprint of that correction. The public release does not. What we have at this initial stage is a profound asymmetry. On one side, a blurry 8-bit single-channel JPEG presented as the best available view of humanity's third interstellar visitor. On the other side, metadata describing a 14-bit, multi-channel, radiometrically calibrated data capture with thermal correction factors. This discrepancy does not automatically prove a cover-up. It does not confirm that NASA hid evidence of artificial origins or anomalous propulsion, but it does, unequivocally, prove that the public explanation is incomplete at best, misleading at worst. It proves that the story of a simple, limited, blurry snapshot is not the story the camera's own data tells about itself. The system is built on trust. The planetary data system exists so that when NASA makes a claim, any researcher on Earth can download the raw data and verify it. The trust is in the openness. But here, the raw files appear to contain references to extensions, channels, and calibration data that never made it into any publicly accessible product. The headers describe a dataset that doesn't seem to exist. Earth Exists isn't claiming they found a smoking gun for aliens. They're claiming they found a smoking gun for data curation. And they are asking a very simple, very reasonable question. Why? Why capture multiband, high-bit depth data of a historic interstellar object and then release only the most degraded version imaginable? Why leave metadata breadcrumbs that point to a richer reality? Why risk the appearance of concealment when the safer, more transparent option would be to explain any technical limitations up front? The stakes here extend far beyond one blurry photograph. If NASA genuinely captured detailed multispectral data of 3i Atlas and chose to release only a token gesture, that decision sets a precedent. It suggests that the data we are shown is subject to editorial decisions we are not privy to, filtered through institutional priorities we do not fully understand. And if the metadata is accurate, if those missing channels exist somewhere in an archive we can't access, then the question becomes far more specific and far more thrilling. What did they really see? We are about to walk through the evidence piece by piece, header keyword by header keyword. We will reconstruct what the raw files actually contain, compare it to what the public received, and measure the exact width of the gap between those two realities. Because the truth about 3i Atlas isn't necessarily locked in a classified vault. It might just be sitting in plain sight, encoded in file structures and calibration logs, waiting for someone to read the fine print that wasn't meant to be read. The chasm between the story, told by a public relations JPEG, and the one written in raw data code can only be understood by walking the path the data itself travels. To grasp why the metadata anomalies around 3i Atlas are so disquieting, you must first understand the journey every pixel captured by a spacecraft like HiRISE is supposed to take. From a photon striking a detector in the freezing vacuum near Mars to the image on your screen. This process isn't magic. It's a meticulously documented pipeline of transformations, and its transparency is what separates open science from a curated performance. The controversy surrounding 3i Atlas thrives in the complexity of this pipeline, in the spaces between file formats and processing stages where data can be altered, compressed, or quietly set aside. The question isn't whether data gets changed on this journey. Every raw space image does. The question is how much gets changed, for what reason, and whether those alterations serve the cause of clarity or the comfort of concealment. HiRISE's raw data begins its life as an experimental data record, an EDR. In mission jargon, these are the digital negatives. They represent the most unprocessed state of the data, a direct dump from the camera's CCD detectors with only the most basic engineering corrections applied. They are messy, noisy, and full of artifacts. Cosmic rays have streaked across the frame, leaving bright, jagged lines. Electronic bias patterns create systematic offsets, a faint grid of non-uniform sensitivity superimposed on the scene. Individual pixels, dead or oversensitive, register nonsense values. This is all normal. EDRs are not meant for public eyes. They are the foundational clay for scientists who possess the tools and knowledge to clean, calibrate, and sculpt meaningful information from the chaos. The next stage produces reduced data records, or RDRs. Here, the calibration corrections are applied in earnest. Dark current subtraction to remove the signal that accumulates from the sensor's own heat. Flat fielding to correct for the fact that no pixel is perfectly uniform. Geometric correction to fix lens distortion. The RDR is a calibrated, cleaned image, its pixel values now in standardized physical units like reflectance. Finally, for deep analysis, this data is often packaged into FITS files, the Flexible Image Transport System, the universal language of astronomy. A FITS file is a bundle. It can contain the primary calibrated image, multiple extension images, like separate red, green, and infrared channels, tables of supporting data, and most critically, a comprehensive plain text header full of metadata describing every aspect of the capture and processing. Outreach images, the ones posted to NASA's website and social media, follow a completely different branch off this pipeline. Public engagement teams take the calibrated science data, the RDRs or FITS files, and simplify them. They compress the file size into JPEGs, adjust contrast and brightness to make faint features visible to the human eye, and sometimes colorize grayscale channels, creating the stunning false color vistas of Mars we know and love. This is not deception, it is communication. Most raw planetary data, before processing, looks like a murky, speckled gray square to anyone but a specialist. The problem, the critical rupture in trust, arises not from the existence of simplified outreach products, but when those products become the only version of reality released to the public. When the raw and calibrated files that should be sitting in the open archive either don't exist, don't match their own metadata, or contain glaring, unexplained omissions. This is precisely where Earth Exists began their forensic excavation of the 3I Atlas observation. Their methodology was systematic. They identified the exact unique product ID associated with the October 2nd observation. They then pulled the entire product set from the Planetary Data System archive. This meant getting everything, not just the solitary outreach JPEG, but every associated EDR, RDR, calibration log, ancillary data package, and header document. They assembled the complete digital dossier of the 3I Atlas encounter as captured by HiRISE. What they found was a folder structure and a collection of files that, upon close inspection, didn't quite add up. The file sizes alone told an initial, suggestive story. EDRs are large because they contain uncompressed detector counts. An 8-bit image is, by definition, half the size of a 16-bit image of the same dimensions, since each pixel uses half the data. If the metadata headers claimed a 14-bit capture, stored in a standard 16-bit container, the file sizes of the raw data should reflect that heavier information load. Earth Exists noted that some auxiliary files in the 3I Atlas set had sizes that sat in an ambiguous middle ground, larger than expected for simple 8-bit data, yet smaller than what a full, uncompressed 14-bit multi-channel capture would produce. This pointed to an intermediate state, data that had been captured at a higher resolution and then selectively downsampled or compressed before archiving. The metadata, a fossil record of the initial capture, preserved traces of what the camera was instructed to do and likely did. The delivered files preserved only what someone decided to keep. The architecture of the FITS files themselves provided the next set of clues. A typical HiRISE observation of Mars, when packaged as a FITS file, is a rich, multi-layered object. The primary header describes the overall observation. When it was taken, where the spacecraft was pointing, exposure settings. Then come the extensions. Often, there are 3 image extensions, one for each CCD channel, the red band data, the blue-green band data, and the near-infrared band data. Each extension is a complete 2-dimensional array of pixel values, a full image in that specific color of light. The file is self-documenting. Open it with any FITS reader, and you can see immediately how many extensions exist and what each one contains. The headers for the 3I Atlas products, according to Earth Exists, described this kind of multi-extension structure. Keywords like Naxis 3, which indicates a third dimension, like multiple image planes stacked together, had values greater than 1, consistent with multiplane data. The filter keyword listed identifiers for multiple bands. Yet, when they opened the delivered FITS files, that complexity was absent. The files contained fewer extensions than their own headers advertised. It was as if the recipe called for a 3-layer cake with distinct flavors, but the delivered box contained only a single, homogeneous slab. Where were the other layers? If the observation plan called for multiband imaging and the headers were populated to expect it, the absence of those bands in the final product required explanation. Were the other channels so hopelessly noisy they were deleted? Was the object only detected in one filter? Or were the extensions processed, analyzed, and then deliberately uncoupled from the public release? The calibration logs deepened the mystery. High-rise data processing involves a series of standardized corrections, each flagged in the metadata. Keywords like dark subtraction, flat field, flat fielding, and radiom cal, radiometric calibration, are set to true or false to indicate which steps were applied. The 3i Atlas headers showed several of these crucial calibration flags set to true. This implied that the pipeline had performed these sophisticated corrections to produce a scientifically usable image. However, the corresponding calibration files, the actual data templates used to perform that dark subtraction or flat fielding, were missing from the archive. This is a significant deviation. Proper scientific practice demands that if you correct your data, you archive the correction parameters so others can verify, replicate, or even undo your steps if necessary. It's the difference between a scientist saying, "I corrected for temperature effects," and providing the exact equation and sensor readings used, versus just asserting the correction was made. The former is verifiable, the latter is an article of faith. Either the pipeline applied corrections without saving the calibration data, a highly unusual and sloppy practice for a mission like Mars Reconnaissance Orbiter, or those calibration files were generated and later removed from the public product set. Then there was the matter of dynamic range compression, a technical term for the brutal simplification that turned whatever high-rise captured into the blur we saw. The outreach JPEG is an 8-bit image. Its histogram, the distribution of brightness values, is crammed into the 0 to 255 range. But if the raw EDR was a 14-bit capture, its pixels held values from 0 to 16,383. Converting that expansive, nuanced range down to the crude 256 levels of a JPEG requires a choice. You can truncate it, brutally chopping off the faintest and brightest signals, or you can apply a non-linear tone curve, compressing the wide dynamic range into the narrow JPEG band. The histogram of the released 3i Atlas image suggests an aggressive tone mapping was used, squashing the presumably faint signal of the interstellar object into the murky middle grays of the 8-bit space. This, in itself, is standard for outreach. You enhance contrast to make something visible. What is not standard is the absence, in the archive, of any higher bit depth version from which this drastic compression was derived. For virtually every other high-rise image of Mars, you can find both the pretty JPEG and the high bit depth multi-channel FITS files. For 3i Atlas, only the JPEG appears to be the final, public-facing product. The high-fidelity originals, if they were ever created, are not where they are supposed to be. Earth Exists also catalogued references in the metadata to specific filter keywords that dangled without corresponding data. High-Rise's 3 primary filters are designated red, BG, blue-green, and NIR, near-infrared. The standard procedure for obtaining color information is to take separate exposures through each filter. The headers for the 3i Atlas observation contain these filter keywords, explicitly naming multiple bands. Yet the sole released product is a monochrome grayscale image, with no indication of which filter, if any, it represents. This creates a series of frustrating, unanswered questions. Were the other filter exposures attempted but failed? Did the object zip through the field of view so quickly that only one filter caught it? Or, as the metadata implies, were multiple filters used successfully, yielding separate images that were then combined, analyzed internally, and excluded from the public dataset? In the language of data forensics, these become missing channels. The term sounds sinister, but in spacecraft data systems, it can have innocent explanations. Sometimes headers reference backup detectors that weren't activated. Sometimes template fields from previous observations linger. But when those missing channels are coupled with other irregularities, the bit depth mismatch, the absent calibration files, the extension count discrepancies, the innocent explanations start to strain under the weight of the pattern. The most perplexing headers of all were those that seemed to belong to a different instrument entirely. Fields labeled with terms like ancil calib chan, ancillary calibration channel, and radiom ref frame, radiometric reference frame, were present. These are not standard high-rise descriptors. They sound like terminology from thermal imagers or spectrometers, instruments designed to measure emitted heat or slice light into fine spectral segments, not broad color snapshots. High-rise is neither. If these fields were mere template artifacts inherited from other instruments on the Mars Reconnaissance Orbiter, they should be empty or filled with default null values. Instead, Earth Exists reported that some contained actual numerical parameters, implying the processing pipeline had populated them with something. What do those numbers describe? What kind of calibration on a visible light camera requires radiometric scaling coefficients typical of heat measuring devices? The group was careful not to overclaim. They hadn't definitively decoded every anomalous field. But they had established that the anomalies existed, that they clustered in this one unusual observation of an interstellar object, and that they stood in stark contradiction to the simple story of a barely captured blur. The metadata for routine high-rise shots of Martian geology are clean, straightforward, and predictable. The metadata for 3i Atlas was cluttered, extra, and oddly suggestive. This forensic deep dive into the pipeline revealed a central, unsettling disconnect. The journey from raw photons to public picture is meant to be a documented, traceable, and open road. For 3i Atlas, that road appears to have forked. One path, the one we were shown, led to a blurry JPEG and a narrative of limitation. The other path, described by the metadata, led toward a richer, multi-dimensional dataset that has, for reasons unknown, been kept out of sight. The archive was supposed to show us everything. Instead, it shows us a gap, and in that gap, a critical question echoes. What travels on the road not taken? To navigate the labyrinth of the 3i Atlas metadata, you need a map of its language. FITS headers are the Rosetta Stone of astronomy, a standardized lexicon that allows a scientist in Tokyo in 2040 to understand the raw pixels captured by an American spacecraft orbiting Mars in 2025. Without this rigid, plain text structure embedded in every file, each dataset would be an inscrutable block of numbers, devoid of context and meaning. The International Astronomical Union established FITS as the universal format precisely to prevent such chaos. It embeds the story of the observation directly into the data. Every exposure time, every filter used, every calibration step applied, the temperature of the detector, the position of the spacecraft, all of it is recorded in simple key-value pairs. The system works because everyone agrees on what the keywords mean and faithfully reports the truth. But when those keywords tell contradictory stories, when they point to data that isn't there, the entire foundation of reproducible science begins to tremble. The forensic investigation into 3i Atlas is, at its core, a meticulous autopsy of these keywords, and the body of evidence they present is speaking a troubling dialect. Let's start with the fundamental unit of information, the bit. The keyword bitpix defines the numerical precision of each pixel. Bitpix, Morse 8, means each pixel is stored as an unsigned 8-bit integer, with values from 0, pure black, to 255, pure white. Bitpix, with 16, indicates signed 16-bit integers, a range from 32,768 to plus 32,767. Bitpix pouch 32 is for 32-bit floating point numbers, used when pixels represent calibrated physical units like reflectance. According to Earth Exists, the headers in the 3i Atlas experimental data records specified bitpix house 16. This is normal and expected for high-rise. The camera's CCDs produce a 14-bit output, but it's more efficient to store this in a 16-bit container, leaving the two highest bits unused. The raw capture, therefore, should have 16 384 possible brightness levels per pixel. The problem is glaringly obvious in the Outreach product. The released JPEG is unequivocally an 8-bit image, somewhere between the bitpix SHAD16 EDR and the public release. The bit depth was halved. Data was discarded. This, in itself, is a standard part of creating a JPEG for the web, but the controversy lies in the fact that this 8-bit version appears to be the only scientifically usable product in the archive. The high bit depth originals, from which this compression was made, are not accessible for independent analysis. The metadata says, "We captured fine detail." The public file says, "Here is a crude sketch." One of these statements is misleading, and the silence from the mission team on which one it is speaks volumes. Next, the dimensionality keywords paint a picture of complexity that never materialized. Naxis tells you how many dimensions the data has. Naxis Nabaus 2 is a simple two-dimensional image, width and height. Naxis section 3 indicates a data cube. This third axis typically represents multiple image planes stacked together, like the separate red, green, and blue layers of a color photograph, or a sequence of images taken over time. The keywords Naxis 1, Naxis 2, and Naxis 3 give the size along each axis. Earth Exists reported that the 3i Atlas headers listed Naxis 3 with a value greater than 1. This is a direct metadata claim that the raw data contained multiple planes, a stack of images. Yet the delivered FITS product, when opened, contained a simple two-dimensional array. The third dimension had vanished. If Naxis 3 exists and is greater than 1, there should be multiple image extensions in the file. Their absence is a direct contradiction between the map, the header, and the territory, the data. It's as if a book's table of contents lists 5 chapters, but you open it to find only 3. The filter or filter ID keyword is equally critical. It identifies which wavelength range was captured. For high-rise, typical values are red, BG, and NIR. A multi-band observation should generate either separate files for each filter or a single FITS file with multiple extensions, each tagged with its filter. The 3i Atlas metadata, according to the forensic analysis, contained filter keyword entries for multiple bands. But the publicly released image is a monochrome smear with no filter identification. If the observation genuinely captured data through multiple filters, those exposures should exist somewhere in the archive. If they don't, if the attempt failed or the data was pure noise, the filter keywords should be blank or set to a single, consistent value reflecting what was actually obtained. Instead, they are populated but orphaned, referencing a multispectral intent that the public-facing data does not reflect. Exposure time records the shutter duration, usually in milliseconds. For a fast-moving target like 3i Atlas, a short exposure would be mandatory to minimize motion blur. Here, the metadata offered another curious hint. Some header fields suggested multiple exposure entries, as if the camera had taken a rapid sequence of frames, a burst shot, rather than a single snapshot. This would be a smart strategy. Capture several quick frames to later align and stack them, increasing the signal-to-noise ratio and potentially allowing for motion correction. But frame stacking requires all the source frames to be present. Earth Exists claimed the headers referenced multiple exposure events, but only one processed, blurry frame appeared in the delivered product. Where are the other frames in the sequence? Were they too smeared or too faint? Or do they exist in a processed stack that was never released? Pipeline history is documented through Boolean flags. Keywords like dark sub, flat field, and radiome cal are set to T for true or F for false. The 3i Atlas headers showed several of these flags set to T, indicating a full suite of calibration corrections had been applied. This is where the chain of custody breaks down. For each of these corrections, there should be a corresponding calibration file in the product set, a dark frame image, a flat field image, that documents exactly what was subtracted or divided out. These are the essential ingredients for the recipe. The 3i Atlas product set, as analyzed by Earth Exists, lacked these critical calibration files. You cannot verify a calibration without knowing what was used to perform it. It's like being handed a financial audit that says accounts were reconciled, but provides no bank statements. Timestamps offer another layer of verifiable chronology. Date OBS is the observation date and time. Date CRE is when the file was generated. These allow anyone to reconstruct the data processing timeline. The 3i Atlas observation was logged for October 2nd, 2025. However, Earth Exists noted that some ancillary files in the product set, calibration logs and metadata manifests, carried creation timestamps earlier than the observation date. This is temporally impossible. You cannot create a calibration log for data before the data exists. The most benign explanation is a database error during archive ingestion or file copying. A less benign possibility is that files from other observations were reused as templates, and their timestamps were never updated, or that files were manually altered or backdated during preparation. While timestamp drift is a known issue in complex systems, its presence in such a high-profile, unique observation adds to the cumulative unease. The BScale and B0 keywords are the scaling factors that convert raw digital numbers from the detector into meaningful physical units. The formula is simple: physical value, Chartres BScale, digital number plus B0. If BScale is 1 and B0 is 0, the raw numbers are already in the final units. If they have other values, it indicates the data has been rescaled or offset. The 3i Atlas headers contained BScale and B0 values that, according to the forensic analysts, did not align with typical high-rise data for Martian scenes. This could indicate a non-standard calibration was applied, tailored for the unusual target. Or it could suggest the data was manipulated post-capture in ways not fully documented in the headers, a departure from standard pipeline behavior. EX name labels individual extensions in a multi-extension fits file. The primary header states how many extensions exist. Earth Exists found that the primary headers for 3i Atlas products referenced extension counts greater than 1, but the actual files contained fewer. This mismatch is a forensic red flag. In a properly managed pipeline, headers are automatically updated when extensions are added or removed. If extensions were intentionally deleted, the header should reflect the new count. If they were never created, the header shouldn't reference them. The persistence of these orphaned references suggests either a broken, sloppy pipeline for this specific product, or a process where data layers were stripped out without updating the descriptive metadata, a process that obscures the file's history. Perhaps the most technically strange findings involve keywords that simply don't belong. Some header fields in the 3i Atlas set, as reported, use terminology associated with thermal instruments or hyperspectral images, devices that measure emitted infrared heat or capture dozens of narrow wavelength bands, not 3 broad ones. HiRISE is neither. It is a 3-channel visible, near IR camera. Why would its metadata contain thermal cal coefficients or spectral calparameters. The charitable explanation is vestigial template values, inherited from other instruments on the Mars Reconnaissance Orbiter that share data processing software. The less charitable explanation is that HiRISE was operating in a non-standard mode, or that its calibration routines captured stray signals, like a faint thermal emission from an outgassing comet, that triggered these specialized correction protocols. The metadata preserves the echo of that event. The public data does not. When Earth Exists performed a comparative analysis, the peculiarity of the 3I Atlas metadata crystallized. They pulled headers from standard HiRISE observations of Martian terrain taken around the same time. Those headers were clean, streamlined, and predictable, with no unusual keywords, no orphaned extensions, no unexplained calibration flags. The 3I Atlas headers, in contrast, were a cluttered attic of extra fields, many of which seemed irrelevant or contradictory. If these fields are meaningless template artifacts, why do they appear so prominently in this one, unique product, and not in the routine ones? If they are meaningful, what do they mean, and why has NASA offered no glossary? The central forensic question thus becomes one of trust. In normal scientific practice, you trust the headers. They are the authoritative documentation. But when the headers themselves are conflicted, when they describe a multiplane, multi-filter, high-bit depth observation that results in a single plane, monochrome, low-bit depth image, which part of the header do you trust? The part that describes the ambitious capture, or the part that is consistent with the degraded release? Verification requires either full access to the upstream raw data, the original 14-bit, multi-channel EDRs, or an official detailed clarification from the mission team that reconciles the contradiction. To date, that clarification has not come. NASA's public statements reiterate the difficulty of the observation and stand by the JPEG as the best available product. They do not address the bitpix mismatch. They do not explain the Naxis 3 value. They do not clarify whether multiband data was captured and excluded, or whether the headers are simply misleading. This absence of technical dialogue is not proof of wrongdoing, but it is pure oxygen for speculation, and it transforms what should be a routine matter of data documentation into a profound question about what we are allowed to know and how we are allowed to know it. The metadata is speaking. We just need someone from the mission to tell us if we're understanding its language correctly, or if we're hearing ghosts in the machine. Every scientific observation has a biography. It is born at the moment of detection, its life chronicled through observation planning, data capture, processing, and finally, public release. This timeline, this chain of custody, is the backbone of reproducibility. It exists not out of bureaucratic habit, but because science demands that any claim can be traced back to its raw origins, each step verified. The biography of 3I Atlas, as reconstructed from public records and archived timestamps, is where the narrative begins to feel less like a straightforward scientific report and more like a story undergoing careful management. The object itself was discovered on July 1, 2025, by the Atlas Survey, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes designed as our solar system's sentinels. Its trajectory was flagged as unusual almost immediately. The math revealed a hyperbolic path, velocity too great to be bound by the sun's gravity. This was no asteroid from our backyard. It was a visitor passing through, the third confirmed interstellar interloper after the enigmatic Oumuamua in 2017 and the comet-like Borisov in 2019. By mid-July, astronomers had refined its course enough to predict where it would be months in advance, and a global campaign began to point every available telescope at it during its brief solar system transit. Among those telescopes was HiRISE, the high-resolution imaging science experiment, orbiting Mars aboard the Mars Reconnaissance Orbiter. HiRISE's day job is geological mapping of the red planet at resolutions fine enough to see boulders the size of a car. It is not an astrophysical instrument. but its pointing system is agile, and Mars's position in late 2025 offered a unique vantage point. A request was approved. On October the 2nd, as 3i Atlas made its closest pass to Mars's orbit, HiRISE would attempt a snapshot. The challenge was immense. The object was approximately 400 million kilometers from Earth, moving at roughly 40 kilometers per second relative to the Sun. HiRISE's field of view is narrow, designed for a stationary planetary surface, not a cosmic bullet. Capturing anything at all would be a feat. The observation was executed, logged, and the data was downlinked to Earth. This much is documented and uncontested. It is in the subsequent timeline, the journey from capture to public consumption, where the chain of custody develops puzzling gaps and curious delays that amplify the questions raised by the metadata. Standard HiRISE turnaround time is a model of efficiency. Raw data downlinks from the spacecraft within days. Initial processing and calibration typically take another week. Outreach image preparation and quality review add a few more days. For a routine Mars observation, the public often sees a processed image within 2 to 4 weeks of the shutter click. For 3i Atlas, the observation occurred on October 2nd, 2025. The processed data files, the EDRs and RDRs, according to their internal timestamps, were generated and placed in the archive by mid-October. This aligns with standard procedure. But the outreach JPEG, the single, blurry image presented to the world as the sole result, was not posted to NASA's public portals until mid-November. A full month's gap exists between the data being processed and ready in the archive and its release to the public. Why? NASA's official statement mentioned the challenge of processing data from an unusual target and the need for additional validation. This sounds reasonable on its face. Pipelines are optimized for Mars, not interstellar flybys. But a 1-month validation period for a single, reportedly poor quality image is anomalous for a mission with HiRISE's streamlined operations. What kind of validation takes 4 weeks? Were scientists arguing over interpretations? Were communications teams debating messaging? Or was there a richer data set that required internal review before deciding what to release? Earth Exists dug into the archive timestamps and found irregularities that complicate the narrative further. They claimed that some auxiliary files in the 3i Atlas product set, specifically certain calibration logs and metadata manifests, carried ingestion timestamps that predated the October 2nd observation. This is a chronological impossibility. A file documenting the calibration of an observation cannot be created before the observation happens. The most innocent explanation is a database error during archive migration or file copying. A glitch where old template files were copied and their timestamps never updated. A less innocent possibility is that files were manually backdated, or that the archive was restructured after the fact, leaving a muddled chronological trail. In forensic terms, a broken chain of custody doesn't prove guilt, but it breaks trust. It means the documented history of the data cannot be taken at face value. The directory structure of the release also raised eyebrows. Public archives typically list files in the chronological order they were ingested. The 3i Atlas product set, however, appeared in a non-chronological sequence. Some auxiliary files, which according to their content should have been generated after the primary data, were listed before them. This could be a trivial artifact of file system indexing, or it could indicate that files were added to the public archive in multiple, separate batches, a possible sign of iterative decision-making about what to include. Perhaps the initial release package was assembled, then revisited, with additional files added or removed, scrambling the order. The context of the release date is also telling. The mid-November announcement coincided with a period of heightened media interest in interstellar objects. Dr. Avi Loeb, The Harvard astrophysicist who had controversially suggested Oumuamua might be of artificial origin had recently published a preprint analyzing 3I Atlas's trajectory. Based on astrometric data from ground-based telescopes, Loeb's team claimed the object exhibited slight acceleration anomalies, not fully explainable by gravity alone. His claims were speculative, but peer-reviewed and headline-grabbing. The timing raises an inevitable question. Did NASA delay the high-rise image release until they could frame it in a way that countered Loeb's more sensational narrative? Did they spend the month between processing and release, not just validating data, but crafting a communication strategy to emphasize the mundane, blurry nature of the encounter, to tacitly argue, see, nothing strange here, just a faint, messy smudge? This wouldn't be malevolent, it would be institutional risk management. After the Oumuamua media frenzy, agencies are wary of fueling what they see as unscientific speculation. But if the released image was curated to support a nothing to see here narrative, while the metadata hints there might have been more to see, then the release is not just data, it's a statement. We are not claiming NASA engaged in deliberate suppression of evidence. We are noting that the timeline deviates from normal procedure, and the absence of a detailed technical explanation for that deviation is conspicuous. If the delay was due to innocent, complex processing challenges, NASA could clarify that with a technical memo. The pipeline failed on the non-standard target. We had to manually reprocess. The other channels were irrecoverably noisy. These are all plausible and acceptable explanations. Instead, the official line remains vague. The image was difficult to process. Validation took longer than usual. This is the best available data. These statements are not lies, but they are not the full, transparent truth the scientific community and the public deserve. They are narrative placeholders. And here is what makes the timeline forensically significant. The gap is a blank space, and in blank spaces, institutional narratives are constructed. The chain of custody is meant to be a transparent, automated pipeline from instrument to archive to public, designed to prevent editorial intervention. Trust in that pipeline is what allows independent verification. But when that pipeline has hiccups, when timestamps conflict, when files appear out of order, when release delays exceed normal parameters, the chain develops weak links. Those weak links might be innocent technical glitches, the inevitable friction of complex systems. Or they might be evidence that someone, somewhere in the process, made conscious decisions about what the public should and should not see. This is not about paranoia. It is about standards. Scientific institutions maintain credibility by following consistent, documented procedures. When procedures are deviated from, even for good reasons, the deviation must be explained and documented. The 3I Atlas timeline contains unexplained deviations. In the absence of that explanation, speculation doesn't just fill the void, it becomes a rational response to opacity. Consider the possible scenarios that could fill that month-long gap. Scenario 1. Internal scientific review. The HiRISE team captured the data, processed it, and found something ambiguous, a spectral hint, a structural suggestion that required careful analysis. They spent weeks modeling, debating, and consulting with other experts before deciding the finding was too uncertain for public release, and that only the bland, blurry image was solid enough to share. Scenario 2. Institutional coordination. 3I Atlas was a global target. NASA may have been coordinating with other space agencies, ESA, JAXA, or ground-based observatories to release complementary data simultaneously. Negotiating such agreements takes time. Scenario 3. External consultation. Given the object's hyperbolic trajectory and high public interest, it is conceivable that entities beyond NASA's Science Mission Directorate were consulted. Planetary protection offices, given the non-zero chance of exotic biological material. National security agencies, given that fast-moving hyperbolic objects share kinematic traits with certain man-made threats? Such consultations would be classified and would certainly delay a public release. Scenario 4. Simple bureaucratic inertia. The image was poor, scientifically marginal, and thus low priority. It sat in a queue until a public affairs officer had time to package it. All these scenarios are plausible. None are mutually exclusive. But they lead to very different conclusions about the nature of space science transparency. The first scenario is cautious science. The second is collaborative science. The third veers into the realm of state secrecy. The fourth is institutional neglect. Without clarification, we cannot know which is true. And this ambiguity is toxic because it forces the public to choose which version of a powerful, taxpayer-funded institution to believe: the meticulous explorer, the cautious bureaucrat, or the secretive gatekeeper. The timeline of 3I Atlas, therefore, is more than a sequence of dates. It is a Rorschach test for trust. The month-long silence between processing and release is not evidence of a cover-up, but it is a period of institutional interiority, a black box. And when that black box's output is a dataset whose own metadata contradicts its presentation, the natural human response is to wonder what happened inside the box. The chain of custody isn't just about proving data wasn't altered, it's about proving the process wasn't altered. For 3I Atlas, the process itself has become the mystery. When the map does not match the territory, when metadata describes a rich landscape and the released image shows a barren plain, we are left to theorize why. Three broad families of hypotheses can explain the discrepancy surrounding 3I Atlas. The first is innocent technical limitation. The contradictions arise from normal, if poorly communicated, data processing constraints. The second is instrument performance failure. The hardware captured more than it could usefully deliver, and the metadata reflects failed ambition. The third is intentional curation. Institutional decisions, for various reasons, shaped what the public ultimately received. All three are plausible. None can be proven without insider access. But by examining the metadata signatures and the context, we can evaluate which hypothesis they best support, and in doing so, we'll see where this story deflates into mundane technical minutiae or escalates into something more profound. Hypothesis 1. Normal downsampling. This is the official stance by implication. Every space mission produces more raw data than can be publicly released in full fidelity. Bandwidth, storage, and public accessibility favor simplified products. HiRise routinely compresses its stunning 14-bit Martian vistas into 8-bit JPEGs for the web. The raw data remains in the archive for scientists. Under this hypothesis, the 3I Atlas metadata is accurate. HiRise captured multiband, 14-bit data as planned. The public received only a simplified monochrome composite because that's standard outreach procedure. The missing channels exist in some internal archive, not because they're hidden, but because they're deemed unnecessary for public consumption. The metadata anomalies, the BitPix mismatch, the Naxios 3 references, are simply artifacts of this compression process, headers that weren't fully updated for the derivative product. Evidence for the process is undeniably standard. The B-scale and B0 values changing between EDR and RDR files is consistent with dynamic range compression. Converting 14-bit data to 8-bit for a JPEG inherently creates a bit depth discrepancy. Collapsing 3 color channels into one grayscale composite would explain the orphaned filter keywords and the missing extensions. If you view the release through the lens of standard public relations, the anomalies seem like predictable byproducts. The fatal flaw. HiRise's archive doesn't usually work this way for unique high-interest targets. For Martian geology, the full multi-channel, high-bit depth FITS files are publicly available alongside the JPEGs. The archive is meant to be comprehensive. For 3i Atlas, a historic third interstellar visitor, only the degraded JPEG appears as the final product. If the raw multi-channel data exists, why is it absent from the public planetary data system? If it doesn't exist, why does the metadata say it should? Normal downsampling doesn't typically involve removing the high-quality source data from the public sphere. It involves adding a low-quality version alongside it. Hypothesis 2. Instrument limitation. This hypothesis accepts that HiRISE attempted the ambitious multiband, high-bit depth capture the metadata describes, but physics intervened. Imaging a faint, fast-moving object at extreme range is brutally hard. Under this scenario, the camera executed its planned sequence, but the signal was so weak that only one channel, likely the red, which HiRISE is most sensitive to, registered anything above the noise floor. The other channels captured only cosmic background and detector static. The multiple exposure attempts resulted in only one frame where the object was even faintly visible. The pipeline processed everything, found the other channels scientifically worthless, and released the single usable frame. The metadata artifacts are genuine but tragic. They reflect what was attempted, not what was achieved. Evidence 4. The released image itself is the strongest evidence. It is extremely grainy, with a terrible signal-to-noise ratio. If this is the best channel, the others would likely be pure noise. The object's speed also supports this. The sequential nature of HiRISE's filters means the object would have moved between exposures, possibly out of the frame for some filters entirely. The references to multiple exposure times could indicate a burst sequence where only one frame caught the target. The fatal flaw. Scientific transparency includes openly discussing failure. If this hypothesis is true, NASA's explanation would be straightforward and would resolve the mystery. They could say, "We attempted multi-band imaging, but due to the target's faintness and speed, only the red band exposure contained a detectable signal. The other channels are noise and are available in the archive for verification." They have not said this. The official narrative is best available image, which ambiguously glosses over whether best means the only one we got or the only one we're showing you. The absence of this clarifying detail is what fuels doubt. Furthermore, if the other channels were pure noise, there's no reason to remove them from the archive. Noisy data is still data. It can be used to characterize the instrument's performance or for advanced noise filtering techniques. Their absence suggests a deliberate pruning, not a simple acknowledgement of failure. Hypothesis 3. Intentional curation. This is the most controversial, but, given the pattern, the most intriguing hypothesis. Here, HiRISE succeeded beyond the public narrative. It captured high-quality multiband data, possibly including a faint near-infrared signature that hinted at unexpected properties, thermal emission from outgassing, or an unusual spectral slope. An institutional review determined that releasing the full data set would invite misinterpretation, fuel uncontrollable speculation, or raise questions NASA wasn't prepared to answer. The decision was made to release only a simplified, ambiguous image, one that satisfied public curiosity without providing enough grist for independent analysis. The metadata anomalies are genuine breadcrumbs, unintentionally left behind because the personnel who prepared the outreach JPEG didn't anticipate forensic scrutiny of the FITS headers. Evidence 4. The pattern of anomalies supports this. It's not one thing, it's the combination. The bit depth compression, the missing multi-channel data, the absent calibration files, the unusual thermal keywords, the extended release timeline, and the timestamp irregularities all point in one direction. A richer dataset was processed and then stripped down. The presence of calibration flags, dark sub-T, without the corresponding calibration files suggests those files were removed. If extensions were simply never created, the flags would likely be false. The fact that the 3i Atlas metadata is cluttered compared to routine Mars observations suggests extra processing steps or non-standard modes were engaged, the records of which were later cleaned from the public product. The fatal flaw. It assumes malfeasance or excessive secrecy without direct proof. It is also the most complex explanation. Institutions are more often sloppy than sinister. The curation could be for benign, even prudent reasons, preventing public panic over ambiguous data, protecting sensitive calibration techniques, or avoiding diplomatic incidents if the data had national security tangential relevance. Intentional curation isn't necessarily nefarious, but it is inherently at odds with open science. So, which hypothesis wins? The metadata alone cannot adjudicate. What we can see is that hypothesis 1, normal downsampling, fails to explain why the high-fidelity source data isn't in the public archive. Hypothesis 2, instrument failure, fails to explain NASA's lack of clear communication about that failure. Hypothesis 3, intentional curation, lacks a smoking gun, but aligns with the aggregated evidence and the extended, opaque timeline. The truth is likely a hybrid, a mix of institutional caution and technical reality. Perhaps HiRISE captured multi-band data. Most of it was poor quality, but 1 or 2 channels revealed a faint spectral hint. Something unexpected but scientifically uncertain. Faced with this ambiguity, and remembering the media firestorm around Oumuamua, NASA made a cautious bureaucratic choice. Release the blandest, least informative version that could still be called a release, and keep the ambiguous data internal for further study. This wouldn't be a conspiracy, it would be risk aversion. But caution without transparency is indistinguishable from concealment. That indistinguishability is the core of the problem. It erodes trust. The scientific method has a built-in mechanism for handling ambiguity, publishing the data with caveats, inviting peer scrutiny. What we have with 3i Atlas is the opposite. The public release of a conclusion, here is the best view, without the underlying data that would allow anyone to assess how that conclusion was reached. The metadata screams that there is more to the story. Until NASA provides the full manuscript or definitively corrects the metadata, the public is left with a cliffhanger. And in that suspense, the darkest interpretations inevitably grow, fed not by evidence of aliens, but by evidence of opacity. The greatest mystery of 3i Atlas may not be what it is, but why the story of how we observed it has become so difficult to read. The distance between raw data and a finished image is a journey of choices. Every pixel on your screen is the product of dozens of mathematical transformations, each optimizing for a priority: noise reduction, contrast enhancement, file size. These transformations are necessary. Raw detector output is often illegible, but every transformation is also a decision, and decisions reveal intent. When an institution releases a single degraded image from a dataset that metadata suggests is richer, we must ask, what would we see if different choices had been made? If we could reprocess the phantom data the headers describe, what might emerge from the noise? This isn't about inventing information. It's about exploring the latent potential in the photons that were captured, potential that might have been suppressed by a pipeline designed for normalcy, not for singularity. HiRISE's standard pipeline is a marvel of automation, tuned for Martian geology. It follows a rigid sequence: dark current subtraction, bias correction, flat fielding, cosmic ray removal, radiometric calibration, geometric correction. Each step cleans the data, but each also makes assumptions. It assumes the signal is from a static, brightly lit, spatially coherent landscape. 3i Atlas was none of those things. It was a faint, moving, point-like source against a dark background. The standard pipeline, designed to filter out noise and artifacts, might have mistakenly filtered out the very signal of interest. A cosmic ray removal algorithm might see a faint, moving streak and classify it as an artifact to be deleted. Aggressive noise smoothing might blur the already tenuous profile into oblivion. This is called conservative processing, erring on the side of removing ambiguous features to produce a clean, reliable image. It's the right choice for mapping rock layers. It might be the wrong choice for extracting every last photon from a once-in-a-lifetime interstellar visitor. So, what could an alternative, target-optimized reprocessing reveal? Let's walk through the possibilities, assuming we had access to the raw 14-bit, multi-channel EDRs the metadata promises. First, bit depth recovery. The Outreach JPEG is an 8-bit compression of a theoretically 14-bit original. Those 16,284 brightness levels per pixel were crushed into 256. Restretching that dynamic range wouldn't create new data, but it would reveal gradients and subtle variations that were erased. A faint hint of a brightness asymmetry across the smudge, a clue to rotation or surface heterogeneity, could be hiding in those discarded levels. What looks like a uniform grey blur in 8-bit might, in 14-bit, show a gradient from one side to the other, suggesting an elongated or irregular shape. Second, advanced noise reduction. The pipeline used on 3i Atlas is nearly 2 decades old. Modern algorithms, especially machine learning-based denoisers, are light years ahead. Trained on millions of astronomical images, they can distinguish between the statistical fingerprint of real astrophysical sources and the patterns of detector noise, or cosmic rays with astonishing fidelity. Feeding the noisy 3i Atlas EDRs into such a network might pull a coherent point source profile from pixels the old pipeline wrote off as garbage. This isn't creating data, it's using better statistics to redraw the boundary between signal and noise. The resulting image might show the object not as a vague smear, but as a compact, if still fuzzy, source with a measurable size and shape. Third, motion deconvolution. The smear is caused by the object's motion across the detector during the exposure. Standard processing averages this into a blur. But if you know the direction and speed precisely, which we do from exquisite astrometric tracking, you can mathematically reverse the blur. This technique, called motion deconvolution, is used in surveillance and planetary radar. Apply it to the 3i Atlas streak, and you could deconvolve the motion kernel, potentially recovering a much sharper point spread function. This could answer a basic question: was it a point source, or was it ever so slightly extended? An extended profile could indicate a coma, a halo of gas and dust, classifying it as a comet. A pure point source would lean toward an asteroidal, inert body. The public JPEG makes this distinction impossible. Reprocessing could make it clear. Fourth, multi-channel combination and spectral analysis. This is the big one. If the metadata is right, and separate red, blue-green, and near-infrared exposures exist, combining them is where real discovery lurks. Even if each channel is noisy, combining them increases the signal-to-noise ratio. More importantly, comparing the object's brightness across these broad bands yields a crude spectral color. Is it redder, bluer, or neutral? A reddish slope could indicate organic rich material or space-weathered rock. A blue slope could suggest ice or fresh material. A bright near-infrared signal relative to visible light could hint at thermal emission from warm dust or gas. A 3-band color composite wouldn't give you a detailed spectrum, but it would place 3i Atlas on a simple taxonomic tree. Is it more like a Kuiper belt object, a comet, a rocky asteroid, or something with an unusual color unseen in our solar system? This single piece of information would be transformative, yet it is precisely the information the monochrome release withholds. Fifth, the thermal ghost. The most speculative but fascinating reprocessing target involves those anomalous thermal calibration keywords. If HiRise's calibration channels recorded something they interpreted as instrumental temperature drift, but which was actually a faint thermal signature from the target, reprocessing that data without applying the correction could reveal it. If 3I Atlas was actively outgassing, the escaping gas, warmed by the sun, would emit weakly in the near-infrared. It might be a whisper, but it's a whisper that could distinguish between an inert rock and an active comet. The pipeline, designed for reflective geology, would have treated this whisper as contamination and subtracted it. Undoing that step is a long shot, but it's the kind of deep forensic analysis open data enables. All of this is hypothetical, because we can't reprocess data we don't have. But that's the point. The potential is what makes the absence so galling. The Outreach JPEG represents one set of choices. Prioritize a clean, simple visual for public consumption. Suppress ambiguity. Compress aggressively. A different set of choices, prioritizing information extraction, would produce a result looking nothing like the blurry smear. It might reveal structure, color, rotation, things the current image deliberately obscures through simplification. You might ask, why wouldn't NASA perform this aggressive reprocessing themselves? They almost certainly did. Mission teams don't release outreach images before exhaustively analyzing the raw data. They know what the EDRs contain. They know what advanced processing could reveal. If they chose to release only the simplified version, that choice was informed by what the full processing showed. And if the full processing revealed something ambiguous, a weird color, a hint of extension, institutional caution would favor releasing the blandest possible version. The accountability gap is this. If advanced processing revealed nothing interesting, NASA could say so and release the data to prove it. If it revealed something interesting but uncertain, they could release the data with caveats, trusting the scientific community to interpret it responsibly. Instead, they released a JPEG with a narrative of limitation. The frustration isn't that data was simplified, it's that they haven't explained what was simplified away. Transparency doesn't require releasing perfect, unambiguous data. It requires releasing honest documentation of what was captured, how it was processed, and what choices were made. The 3I Atlas metadata is that documentation, and it hints at a richer reality. If that richer data exists, even as a noisy, ambiguous shadow, it belongs in the public archive. If it doesn't, the metadata should be corrected. This middle ground, where metadata promises more than the images deliver and the institution stays silent, is where mistrust germinates. And this isn't just about one image, it's about precedent. If NASA can selectively release simplified data for historic interstellar objects without full documentation, what stops them from doing the same for the next one, or for a potential Mars biosignature? When institutions become gatekeepers of what data is safe for public consumption, science stops being a collaborative, reproducible endeavor and starts being an authoritative presentation. Authority without transparency is indistinguishable from control. The reprocessing we can't do symbolizes the science we're not allowed to participate in. A central question grounds the entire metadata mystery. Can high-rise even do what the headers suggest? Instruments have hard physical limits. High-rise was built for one purpose: to photograph Mars in stunning visible and near-infrared detail. It's a geologic imager, not an astrophysical spectrometer or a thermal camera. So when its metadata hints at multi-band spectral imaging and thermal calibration, we must perform a sanity check. Is this capability within its design? And if it is, what would that data actually look like? And would it be scientifically meaningful or just noise? High-rise's optical design is key. It doesn't have one sensor. It has 3 separate CCD arrays, each behind a different filter. The red band covers roughly 550, 850 nanometers, peaking in the orange-red. The blue-green, BG band, covers 400, 600 nanometer. The near-infrared, NIR, band covers 800, 1000 nanometer. These are not narrow spectral windows. They are broad swaths of light, each hundreds of nanometers wide. This is not spectroscopy, which slices light into fine segments to reveal atomic fingerprints. This is crude color vision, 3 broad samples of the spectrum. It's enough to tell a red volcanic rock from a blue-green mineral deposit on Mars, but not enough to identify specific molecules. So, multi-band imaging for HiRISE means just that: 3 separate grayscale images in red, blue-green, and near-infrared light. Combine them, and you get a false-color composite that can enhance subtle differences. This is routine. The critical complication is time. HiRISE's 3 CCDs are not side by side looking at the same spot simultaneously. They are arranged in a line along the spacecraft's ground track. As the Mars Reconnaissance Orbiter flies over the planet, the ground passes first under the red CCD, then a fraction of a second later under the blue-green CCD, then under the NIR CCD. For a static Martian landscape, this works perfectly. The images are perfectly aligned because the ground is stationary relative to the spacecraft's predictable motion. But for 3I Atlas, a target moving independently at kilometers per second, this sequential capture is a deal breaker. The red CCD might catch the object at one point in the frame. By the time the blue-green CCD looks, the object has moved. By the time the NIR CCD looks, it may have moved out of the frame entirely. The resulting 3 images would show the object in 3 different positions, making them impossible to combine into a coherent color picture. The multiband data would be scientifically useless for determining color, unless the object was miraculously slow or the exposure was incredibly short. This provides a compelling, innocent explanation for the metadata anomalies. The observation plan would have called for a standard multiband sequence. The headers were populated accordingly, but in execution, only one channel, likely the first, the red CCD, captured the object in a usable way. The other channels either missed it entirely or caught a smear in a different location, rendering them worthless for spectral analysis. The pipeline archived the headers as planned, but the valuable data products from the other channels were never generated for release. This fits hypothesis 2, instrument limitation. The metadata promises color. Physics delivered a monochrome blur. But what about the thermal keywords? This is where the instrument reality gets weird. HiRISE is definitively not a thermal imager. Thermal imaging detects mid to far infrared radiation, wavelengths of 3 to 15 microns, the kind emitted by objects at room temperature. HiRISE's NIR band stops at 1 micron. It's utterly blind to true thermal emission. So, why do terms like thermal cal appear? 2 possibilities dominate. First, template inheritance. The Mars Reconnaissance Orbiter carries other instruments, like the CRISM spectrometer, which have more complex calibration needs. The software pipeline that packages HiRISE data might use a common template header that includes fields for all instruments. And these thermal fields are meaningless, vestigial entries for HiRISE. They should be empty or null. If they contain numbers, it could be a software bug. Second, and more intriguing, is calibration artifact. All CCDs are sensitive to their own temperature. Their dark current, noise, increases with heat. To correct for this, instruments have internal temperature sensors and apply corrections based on calibration curves. This is thermal calibration, in the sense of calibrating the instrument's thermal noise, not imaging the target's heat. The metadata keywords might refer to this internal housekeeping. The confusion arises because the same terminology, radiometric scaling, thermal correction, is used for both correcting instrument noise and measuring target emission. But let's entertain the uncomfortable, remote possibility. HiRISE's NIR band, while not a thermal imager, is sensitive to wavelengths where very hot objects or certain molecular emissions can glow. If 3I Atlas was an active comet, the gas in its coma, excited by sunlight, can emit specific emission lines in the near-infrared. This is not blackbody thermal emission, it's fluorescence. It's faint, but detectable. If HiRISE's NIR channel caught a whisper of this, the automated pipeline tuned for reflective surfaces, might have flagged the unusual signal as an instrumental artifact, like a bad column or temperature drift, and applied a correction to remove it. The metadata would log this correction with terms like thermal cal or radiome cal, and the corrected data, with the emissions subtracted, would be archived. The original signal would be gone. This is speculative, but it's not impossible. It would mean the pipeline accidentally erased a real scientific signal because it didn't fit the expected pattern for a Mars rock. The bottom line on capability: HiRISE is capable of multiband imaging, but its sequential method makes it nearly useless for fast-moving targets. It is not capable of true thermal imaging, but its calibration systems might use thermal terminology for internal noise control, and its NIR band could, in theory, detect faint emission lines from an active target. Therefore, the metadata references are plausible, but require careful context to interpret correctly. They could mean a failed multiband attempt, innocent; standard internal temperature calibration, innocent; a non-standard detection that triggered unusual calibration steps, highly interesting. The problem, once again, is the absence of that clarifying context from the only entity that can provide it, the mission team. Without it, we are left with a Rorschach test of acronyms. To a casual observer, thermal calibration on a visible light camera sounds like a shocking discrepancy. To an instrument engineer, it might be a Tuesday. The ambiguity itself is the issue. It allows the gap between public narrative and technical reality to persist. And in that gap, the most extraordinary interpretations find space to grow, not because they are likely, but because the ordinary explanations have been left unsaid. By not clarifying the mundane truth, NASA allows the extraordinary speculation to become the default narrative for a growing number of people. The instrument's reality is knowable. The failure to communicate that reality is a choice. Venturing into metadata forensics is like navigating a minefield where most of the suspicious-looking bumps are just old, buried pipes. For every genuine anomaly, a dozen innocent artifacts can mimic deception to the untrained eye. File formats accrue digital cruft over decades of software updates. Pipeline templates carry vestigial fields from obsolete instruments. Timestamps get mangled during server migrations. Checksums fail due to bit rot, not tampering. It is dangerously easy to download a FITS file, see an unexpected keyword, and cry, cover up. The real forensic challenge, and the core of the scientific method, is distinguishing signal from noise. Which anomalies are routine technical debt, and which are genuine red flags, demanding explanation. To understand the 3i Atlas case, we must rigorously apply this filter. Common forensic pitfalls. Template fields. Spacecraft software is built on inheritance. A new mission uses code and file formats from its predecessors. Consequently, FITS headers often contain keywords defined for other instruments or older missions. These fields persist as defaults, filled with zeros, nulls, or NA. If you don't have the mission's data dictionary, the document specifying which keywords are active, every unexpected field looks like hidden data. The thermal keywords in the 3i Atlas headers, thermal cal, radium ref, are prime suspects for being template noise. Extension count mismatches. A FITS header may allocate space for 5 extensions, but only 3 contain data. The other 2 might be empty placeholders, diagnostic slots, or reserved for future use. Some FITS readers might not even display empty extensions. An amateur seeing NAXIS 3 Rata 3, but only 1 image array might assume 2 were deleted, when they may have never been populated. This is a classic misinterpretation. Filter keyword. Orphans. An observation plan calls for red, BG, and NIR filters. The planning software populates the filter keyword with all 3. During execution, only the red filter succeeds. The keywords remain, describing intent, not outcome. This is sloppy but common documentation, not evidence of missing data. Timestamp drift. In complex data systems, files pass through multiple servers and archives. The date KRE might reflect creation on the spacecraft, ingestion on Earth, or copying to the public server. If any system clock is off, or if files are batched for processing days later, timestamps will be inconsistent. A file appearing created before it was observed is often a synchronization glitch, not a time-traveling conspiracy. Checksum mismatches. FITS files can include datasum and checksum keywords, hash values that verify file integrity. If they don't match, the file was altered after the checksum was calculated. But the alteration could be benign. A bit flipped during transmission, file corruption during storage, or a format conversion that changed padding bytes. It indicates a broken chain of custody, not necessarily malevolent tampering. Genuine red flags. So, what would constitute a signal strong enough to rise above this noise? A genuine red flag is an anomaly that cannot be easily dismissed as a common artifact. The forensic standard might include violated causality, files with creation timestamps legitimately earlier than the observation date and containing target-specific data, not template files. A calibration file generated for 3i Atlas on September 1, 2025 would be impossible and suspicious. Logical inconsistencies, filter keywords explicitly populated with specific band names, combined with file sizes inconsistent with single band capture. If a file is 10 metadatas and a single band 8-bit image of its dimensions should be 2 MB, something else is in there. Missing pipeline documentation. Calibration flags set to true, dark subit, flat field T, with the corresponding calibration data files completely absent from the archive. This breaks the fundamental rule of reproducible science. You must archive the corrections you apply. Phantom data products, metadata, describing specific complex data products, e.g. spectral cube, that do not exist anywhere in the public archive and are not mentioned in any mission documentation for that instrument. Patterns, not isolates. Multiple independent anomalies all pointing in the same direction. One odd keyword is a quirk. 5 different quirks all suggesting more data was captured than released, form a pattern worthy of investigation. Evaluating Earth exists claims against this standard. Let's apply the standard to the core findings from the 3i Atlas metadata. Bit depth mismatch, bitpic squarg 16 versus 8-bit JPEG. Strong, but not definitive. This is expected in outreach. The red flag isn't the compression itself, it's the absence of the high bit depth source in the public archive. This elevates it from standard practice to a potential omission. Multiband keywords. Without data, moderate, easily explained as a failed observation. The red flag is heightened by the lack of a clear statement from NASA that the other bands failed. Silence turns a likely innocent artifact into a persistent question. Thermal calibration keywords. Weak on its own, highly likely to be template inheritance. Becomes slightly more interesting if these fields contain unique numerical values not seen in other high-rise headers. Timestamp anomalies. Moderate, very common in archives, but their presence adds to a cumulative sense of a messy, non-standard data release process for this unique target. Extended release timeline. Circumstantial, could be benign review. Becomes a red flag when combined with the above. The timeline is the context that makes the data anomalies more suspicious. The power of the pattern. Here is the forensic pivot point. None of these anomalies, in isolation, is a smoking gun. Each can be argued away. But forensic science, like astronomical signal detection, often deals in probabilities, not certainties. The aggregate of these issues forms a pattern. 1 anomaly is chance. 3 are coincidence. 5 independent lines of evidence, all leaning toward the same conclusion, that the observed reality, a blurry JPEG, does not match the documented capture, multiband, high-bit depth, create a signature. That signature doesn't prove intentional curation, but it creates a statistically significant deviation from the expected norm that demands an explanation. The counterargument: complexity is not conspiracy. The strongest counter to the pattern argument is the sheer, breathtaking complexity of a decades-old space mission. The Mars Reconnaissance Orbiter has been operating since 2006. Its software has been patched, updated, and modified countless times. Different instrument teams use slightly different standards. File format conversions introduce artifacts. Archive migrations corrupt metadata. If you scrutinize the headers of every high-rise observation with the same fervor applied to 3i Atlas, you'd probably find similar quirks in many of them. The 3i Atlas anomalies might not be unique. They might just be the first time anyone looked this closely at a non-Mars target. This is why definitive forensic conclusions require comparison datasets. Earth Exists claims they compared 3i Atlas metadata to contemporaneous Mars observations and found the Interstellar Objects files had more irregularities. This claim is critical. If true, 3i Atlas is an outlier and the anomalies are significant. If false, if similar quirks are littered throughout the archive, then the 3i Atlas metadata is unremarkable. Verifying this requires a crowdsourced audit, downloading dozens of high-rise products from the same period, parsing their headers, cataloging extension counts, filter keywords, and timestamp patterns, and performing a statistical analysis to see if 3i Atlas truly sits outside the norm. This is the kind of work open data enables, but it is labor-intensive. The forensic gap and the burden of transparency. We are left in a forensic gap. The evidence is suggestive, not conclusive. It creates enough suspicion to demand an explanation, but not enough proof to compel one without institutional cooperation. This gap is where public trust evaporates. In a court of law, the burden of proof is on the accuser. In the court of public scientific trust, the burden of transparency is on the institution. NASA, as the producer and publisher of the data, holds the key to the context needed to interpret it. They can release the data dictionary that explains which keywords are templates. They can issue a report explaining the 1-month processing delay. They can state clearly, "We attempted multi-band, but only the red filter caught the object. The other data is noise and is available at link." Or they can release the full multi-channel dataset and let the chips fall where they may. Their continued silence on these specific technical points is, in a way, its own form of data. It is data about institutional priorities. It suggests that clarifying these discrepancies is less important than maintaining the simple, controlled narrative of the initial release. And that, in the end, may be the most genuine red flag of all. Not in the metadata, but in the void that surrounds it. The gaps in explanation are becoming louder than the data itself. When you are exploring the unknown, the one thing you must bring with you is credibility. For 3i Atlas, that credibility is now entangled in a mess of ambiguous keywords, waiting for someone with the authority to clean them up. If we entertain the possibility that the 3i Atlas data release was intentionally curated, that a richer dataset was captured, and a decision was made to publish only a degraded subset, the immediate question is why? Institutions are not monoliths with singular motives. They are complex organisms that respond to incentives, pressures, and constraints. Understanding plausible motives doesn't require believing in a grand conspiracy about alien technology. It requires a clear-eyed look at how large, publicly funded scientific agencies actually operate when faced with ambiguous, high-profile data that could be easily misinterpreted by the public, the media, or geopolitical rivals. The motives are often a blend of the prudent, the political, and the protective. Motive 1. Public narrative management. The memory of Oumuamua is a ghost in the machine of interstellar object studies. That first visitor sparked a global firestorm of speculation. When a tenured Harvard professor like Avi Loeb publishes a peer-reviewed paper suggesting an artificial origin, it legitimizes front-page headlines asking, "Is it aliens?" NASA, as the world's most visible space agency, bears the brunt of public expectation and scrutiny. The experience taught a hard lesson. Ambiguous data plus a hungry media, a narrative cyclone that can detach from scientific reality for years. With 3i Atlas, if HiRise's multiband data revealed any spectral oddity, a strange color, a hint of non-cometary composition, the agency would face a communication nightmare. Release the raw data and watch the cyclone form again. Withhold it completely and face accusations of a cover-up. The middle path, the path of least institutional risk, is to release a single, ambiguous, low-information image. It fulfills the obligation to share, but provides no fuel for sensationalism. It says, "We looked. It's faint. Move along." This isn't malicious. It's crisis aversion. It's the motive of an institution that has been burned by public misinterpretation and seeks to control the story. Motive 2. Planetary protection ambiguity. This motive exists in the dry language of international treaties. The Outer Space Treaty and NASA's own planetary protection guidelines mandate caution regarding biological contamination. While an interstellar object is fantastically unlikely to harbor life, its very origin outside our solar system means its chemistry is unconstrained by our planetary history. If the spectral data from HiRise suggested complex organic chemistry or other biosignature adjacent features, even if explainable by abiotic chemistry, it would trigger a formal planetary protection review. Such a review would be internal, cautious, and likely slow. Releasing data that prompts public questions about alien life before the agency has completed its own protective assessment would be seen as irresponsible. Withholding the data until the review concludes it poses no risk, or until the object is far away, is standard bureaucratic procedure. The motive is not to hide life, but to follow legal and ethical protocols to the letter, even if those protocols create an opaque delay. Motive 3. Instrument performance embarrassment. HiRise is a flagship instrument, a technological marvel. Its stunning images of Mars are a cornerstone of NASA's public appeal. What if it failed on a high-profile target? Not a complete failure, but a performance so poor that the raw data was a chaotic mess. The metadata describes a capable capture, but the reality in the pixels might have been disastrously noisy. Releasing that raw data would allow anyone to see how badly the camera struggled with a non-standard task, potentially embarrassing the engineering team and giving ammunition to critics who question the mission's cost. It's far safer to release a heavily processed, cleaned-up JPEG that says, "We got it," than to release the raw files that whisper, "We barely got it, and it was a mess." The motive is reputational protection, defending the legacy and perceived competency of a billion-dollar mission. Motive 4. Institutional communication philosophy. Modern NASA is not the NASA of Apollo. The agency has evolved a more cautious, peer-review-centric model for data release. Preliminary findings are validated internally before public announcement. Ambiguous results are clarified and contextualized. This is, in principle, good scientific practice. It prevents the spread of incorrect information. But it creates a bottleneck where institutional gatekeepers decide what is validated enough for public consumption. The 3i Atlas data, with its likely poor signal-to-noise ratio, would fall squarely into the ambiguous category. The internal review might have concluded, "We can't say anything definitive from this, so we shouldn't say anything at all except show the picture. This motive isn't about hiding. It's about a paternalistic view of science communication that believes the public cannot handle uncertainty and must be presented with polished, interpreted conclusions, not raw, challenging data. Motive 5. National security adjacency. This is the most sensitive motive. Objects on hyperbolic trajectories are, kinematically, identical to certain types of fast-moving human-made objects. The US Space Force and other defense agencies have a vested interest in tracking anything entering near-Earth space. While 3i Atlas was never near Earth, its detection likely triggered routine notifications within the national security apparatus. If the high-rise data, particularly any non-standard calibration data, contained information about the object's optical properties that could be relevant to satellite tracking or missile defense technologies, that data could be subject to temporary classification for review. This isn't about the object being an alien probe, it's about the data having potential dual-use applications. NASA, as a civilian agency, would be legally obligated to comply with such a review. The motive is not conspiracy, but adherence to national security law, a realm where transparency is explicitly not the priority. Historical precedent. Caution, not cover-up. It is crucial to view these motives through the lens of history. NASA has a long record of cautious, not covert, data handling. The Viking lander life detection experiments in the 1970s produced famously ambiguous results. The agency spent decades carefully reanalyzing that data before converging on a mostly non-biological explanation. The Martian meteorite, ALH 84001, which in 1996 was announced to contain possible fossil evidence, sparked a frenzy. NASA learned that announcing provocative but uncertain findings can backfire, damaging scientific credibility. The pattern is not one of hiding truths, but of managing the interface between uncertain science and a public that craves certainty. Institutions hate ambiguity because it leads to controversy, which leads to political scrutiny and funding threats. The safest strategy is to avoid releasing ambiguous data until it can be packaged with enough context to prevent misunderstanding. This is how bureaucracies survive. The tension, science versus institution. This creates the fundamental tension at the heart of the 3i Atlas case. The scientific ideal demands raw data be released immediately. Science advances through independent verification, serendipitous reanalysis, and the collective intelligence of the global community. The institutional reality often demands data be released carefully. Public trust, the agency argues, can be eroded by premature or misinterpreted findings, which in turn jeopardizes future funding and political support. Both priorities are, in their own way, legitimate. The scientist wants truth. The institution wants stability. The conflict arises when institutional caution becomes so paramount that it morphs into information control. We cannot know which, if any, of these motives apply to 3i Atlas, but their plausibility is what makes the silence so resonant. If the motive was pure, mundane caution, explaining it would be easy and would rebuild trust. The data was very noisy and ambiguous. We didn't want to create a misleading narrative, so we released only the clearest composite. The full noisy data is here. The fact that such a statement has not been made suggests the motives may be more complex, or that the institutional culture of caution is so ingrained that explaining itself is not seen as necessary. This is the real cost of opacity. It doesn't just hide one dataset, it poisons the well for all future ones. Once suspicion takes root, every future release, every future best available image from the frontiers of space will be met with a new corrosive question. Is this really all there is? Trust is cumulative. Erode it once, and every subsequent action is reinterpreted through the lens of potential concealment. For an agency whose mandate is to explore the unknown for all humanity, That is a fate far worse than a messy, ambiguous data release. You have now journeyed through the layers of the 3i Atlas mystery, from the pixelated smear released to the public, down through the cryptic metadata, into the pipeline that processes reality, and through the institutional labyrinths that might govern what we see. We've weighed technical limitations against the possibility of curation. The goal of this final part is not to tell you what to believe, but to hand you the tools to become an independent auditor of these claims. The only way a story like this resolves is if enough people look at the evidence themselves, creating a collective pressure for clarity that institutions cannot ignore. The truth about 3i Atlas is not in a video or an article, it's in the publicly downloadable files waiting for verification. A viewer's checklist for verification. Download the data. Go to the NASA Planetary Data System, PDS, website. Search for high-rise observations from October 2025. Find the product ID for the 3i Atlas observation, often linked from press release materials. Download the entire product set, the outreach JPEG, the EDR files, the RDR files, and all ancillary calibration and metadata documents. Do not rely on screenshots or secondhand summaries. The raw evidence is a click away. Open the FITS headers. You will need a FITS reader. Free software like SOImage DS9 or Python libraries like Astropy work perfectly. Open the EDR, experimental data record files. Examine the primary header. Look for these critical keywords and write down their values. Bitpix, the bit depth. Is it 16? Indicating 14-bit data stored in a 16-bit container. Naxis, Naxios 1, Naxios 2, Naxios 3, dimensionality. Does Naxios 3 exist, and is it greater than 1, suggesting multiple image planes? Filter or filter ID. Which filter bands are listed? Red, BG, NIR. Exposure. Time. What is the recorded exposure duration? Date OBS, the observation date and time. Date CRE, the file creation date and time. Compare these values to the outreach JPEG. The JPEG will have none of this metadata. The discrepancy between Bitpix SART16 and an 8-bit JPEG is your first tangible data point. Check extension counts. The primary header states how many extensions exist. Open the file and manually count the image extensions. In DS9, they appear as separate frames. Do the numbers match? If the header says there are 3 extensions but you only see 1, document it. Look for Xname keywords that label each extension, e.g., red channel, BG channel. Are they consistent with the filter keywords? Examine calibration flags. Search the headers for Boolean flags, dark subtraction, flat field, flat fielding, radiom cal, radiometric calibration. If these are set to T for true, it means these corrections were applied. Now, look in the downloaded product folder for the corresponding calibration files, usually with names containing dark, flat, or specific calibration tables. Are they there? If flags are true but the files are missing, note it. Compare timestamps. Look at date OBS and date CRE. The creation date must be after the observation date. If it's not, that's an anomaly. Check the timestamps on all files in the product folder. Do any auxiliary files have creation dates before October 2nd, 2025? If so, which ones and what do they contain? Search for anomalous keywords. Scan the headers for terms that seem out of place for a camera. Thermal cal, radiom ref, spectral, emission. Note if these fields contain numerical values or are null, 0. Are they active parameters or empty templates? Analyze file sizes. Do a simple check. An 8-bit image size is width, height, bytes. A 16-bit image is roughly twice that, ignoring compression. Calculate the expected size for a single-channel image based on the dimensions in Naxios 1 and Naxios 2 and the Bitpix value. Does the actual file size of the EDR match the expectation for 16-bit data? Is it somewhere in between, suggesting compression? Inspect BScale and B0. These keywords convert raw numbers to physical values. Note their values in the EDR and the RDR. Significant changes indicate rescaling or compression was applied during processing. Verify checksums, if present. If the headers contain datasum and checksum keywords, use your FITS reader to compute the checksum of the current file data and compare it to the header value. A mismatch means the file was altered after the checksum was made. Note the result. Perform a baseline comparison. This is the most important step to separate signal from noise. Download the product sets for 2 or 3 routine high-rise observations of Mars from the same time period, October-November 2025. Repeat steps 2 to 9 on these normal files. Create a simple table or spreadsheet comparing the key header values. Does the 3i Atlas product have unique keywords? Does it have missing extensions where the Mars observations have them? Are its timestamp anomalies present in the others? This comparison tells you if 3i Atlas is an outlier or just typical of high-rises' occasionally messy metadata. Document and share. Take screenshots of key header sections. Save text dumps of the keyword lists. Record your file sizes and timestamp findings. Compile your observations into a clear, shareable document. A Google Doc, a GitHub README, a post on a forum like Cloudy Nights or Reddit's R Astronomy. The goal is reproducibility. Your work should allow anyone to follow your steps and confirm your findings. Seek expert context. If you find something you don't understand, ask. Post your findings online and tag knowledgeable people. Email the high-rise team's public contact address with specific, polite, technical questions. Most scientists appreciate engaged curiosity if it's respectful and evidence-based. Don't lead with accusations, lead with observations. I was examining the headers for product ID X and noticed Y. Can you point me to documentation explaining this? What constitutes proof? Manage your expectations. Metadata anomalies alone are circumstantial. They create questions, not convictions. Definitive proof of data withholding would require something like an insider providing internal data products with clearly more detail. A successful Freedom of Information Act, FOIA, request yielding previously withheld files. Independent observations from another telescope, e.g., JWST ground-based spectroscopy, that directly contradict NASA's characterization of the object's properties based on the released image. A checksum verified finding that public files were altered post-creation in ways inconsistent with standard archive maintenance logs. The stakes, beyond one blurry image. This exercise is about more than 3i Atlas. It is a test case for the principles of open science in the 21st century. We are at a crossroads. On one path, space exploration remains a collaborative, transparent human endeavor, where data is a public trust and discovery is a participatory process. On the other path, it becomes a series of curated presentations, where institutions act as gatekeepers, deciding what the public is ready to see, filtering reality through layers of risk assessment and narrative control. The 3i Atlas metadata saga, at its heart, is about who gets to narrate our encounter with the unknown. Is it only the official voices, with their press releases and simplified JPEGs? Or is it also the distributed network of curious minds, the archivists, the coders, the amateur astronomers, who believe that the data, in all its messy, ambiguous glory, belongs to everyone? By taking the steps outlined above, you become part of that network. You move from being a consumer of a story to a verifier of evidence. NASA could resolve this today with a technical memo. They could release the full data stack. Their choice not to do so is a choice in itself. In the absence of their explanation, the only recourse is independent verification. So, go to the archive, download the files, open the headers, Check the timestamps. Compare the data. Your curiosity is the most powerful tool for transparency we have. What you find might support the narrative of institutional caution. It might reveal simple, boring errors. It might uncover something we haven't even considered yet. That is how science works. That is how trust is built, one verified fact at a time. The truth about 3i Atlas isn't hidden, it's encoded. And the key is in your hands.